Recorded is rolling. It is Wednesday, March 13th. A bunch of guys just signed on to Kahoot. We're going to flip over and do that real fast. So conceptual questions related to relativity. I did not print those out this time, but I did post those to Google Classroom if you wanted to follow along. Right. And then yesterday we did most of these algebra-based questions, so we're going to do the rest of them today, number 7 through 11. I'm going to have you guys hold on to this paper because there's a different question on the back. Oh, it's a speed of light puzzle, like Piso's cogwheel. Right, that there. Right, and then, oh yeah, we have no school on Friday, right, so we'll have to. All right. So let's switch over here to Kahoot. You guys ready for some conceptual questions about relativity? Right. In contrast to an object with mass, no matter how fast the source of light is moving, light always. Yeah, has the same speed, right? All right, so just to remind you guys, reorient you guys back into physics, what you guys see in the last couple of days. That's in contrast to classical Newtonian relativity. And there's one of those questions coming up later on. It's like way later. There is one Newtonian relativity question. Right? And my example for that is like if you're in the back of a truck and you throw a baseball and the truck is moving, it's like, okay, well, how fast is the baseball going? Well, it depends. Is it relative to the person throwing it in the back of the truck, or is it relative to somebody standing on the ground on the side? Because those two different velocities, right? Right. But if both those people did a speed of light experiment, like they're measuring what is the speed of light of like the light beams from the truck, they'll get the exact same speed. Right. Remember Einstein's interpretation of that was, well, the only way to make that consistent is there has to be a time dilation, among other dilations. All right, we're off to a good start. Points on the board. And number 2, Einstein reasoned that yeah, all the above. All those statements are a little bit different rephrasings of the same idea they're getting at. So all motion is relative. Like how fast are you going? Well, let's look at this gold answer. Say a spaceship in space. How fast is a spaceship in space going? Well, it can really only measure relative to other objects like nearby planets, not relative to empty space. There's no such thing. There's no another idea that kind of goes hand in hand with that is there's something called a cosmological principle, and an idea related to that is there's no such thing as the center of the universe, or you could say kind of like the center of the universe is kind of everywhere, right? It's not like everything's moving away from a central point, except everything's moving away from everything somewhere, right? All right. It can only measure your speed relative to other objects, not to empty space. Got Zach, A-Rod, Burger Place, JP, and Mackenzie. Reading time. A spaceship moves away from a space station at half the speed of light. If a person in the space station flashes a light beacon, people in the spaceship will see the light traveling toward them at a speed of. Yeah, the speed of light. The speed of light. Okay. This right here is Einstein relativity. Now, if you asked Isaac Newton the same question, Isaac Newton probably would have guessed the blue one, right? Because that's Newtonian relativity, right? You throw a baseball at so fast, but you're on a moving truck. Okay, well, you know, now you got to add or subtract velocities, right? Right, which would kind of tend you towards the blue answer. But no. Yeah, light. Everybody agrees on what the speed of light is, regardless of your frame of reference. All right, JP, top spot. More reading time. Suppose we observe a spaceship whizzing past us at a very high speed. Compared to what the person in the spaceship sees, we see the spaceship clock is running. Right, so we're looking through a telescope through the spaceship window. Their clock. That clock running what? Sound like twin paradox. Yeah, slow. All right. Yeah, you guys do remember twin paradox. So you guys remember Earth twin, rocket twin started out the same age. Rocket twin flew at a relativistic speed and stayed young. So like, oh, only years passed, but Earth twin grew long white beards. It's been 20 years. Yeah. Now remember, if you're along for the ride with rocket twin, you don't notice anything strange inside the ship. But Earth twin and rocket twin look at each other through a pair of telescopes. They see each other's clocks ticking at different rates. If you're moving at a high-speed spaceship relative to Earth, you would. Ooh, if you're inside the ship yourself, all along for the ride, yeah, you don't notice anything weird about your own locality, right? For clocks to slow down, that takes Earth twin observing rocket twin, right? Right, looking through a telescope, right? As long as you're on board the ship, everything to you is perfectly fine in your own locality. Right? All right, got Zach, Mackenzie, A-Rod, Burger Place, JB. According to special theory of relativity, all laws of nature are the same in. Yeah, there you go. Reference frames that move at constant speeds. Another term you'll hear that's synonymous with that is called inertial frame of reference. So inertial frame of reference could be either at rest or constant speed. Right? Oscillation does involve acceleration. Maybe that's a hint why it's either one of those. Thank you. Clocks on a spaceship move. Okay, so the spaceships move very fast. So the clocks appear to run slow when viewed. Yeah, from Earth, right? So this is Earth twin looking through a telescope through rocket twin's rocket window, right? All right, twin paradox. Ooh, we got a winner. Zach on fire. A-Rod, JP, Burger Place, 12. You're actually looking into the past when you look at, right, is what's technically true. Technically true. Yeah, okay, that's what I'm looking for. I pull all these questions from basic questions from Paul Hewitt. Right? So yeah, it's all this one. He was going with this answer. All right, I'll just keep that too. So definitely starlight is definitely true, right? Because if there's a star that's 10 light years away, then you're seeing the starlight from 10 years ago. You're definitely seeing that in the past. But really anything you look at, if there's a physics book that's 2 feet from your face, it takes a tiny, tiny, tiny amount of time for the light from that surface to reach you. So really anything you look at, you're looking at a little bit into the past. Fun to think about, right? All right, Mackenzie, hop in the top 5, Burger Place 12, still in the lead. When you approach a light source, the wavelength of emitted light appears. Ooh, about the Doppler effect. For Doppler effect, so you're headed towards this light wave. Yeah, shorter, right? So you head towards something. You guys are in a Doppler effect. There's a sound version of it. There's a passing car, but there's a light version too, right? So, shorter wavelengths. That's a higher frequency. That's also called blue shifting. Blue shifting, right? Now, if you look out into the night sky, as almost all galaxies relative to us are shifted how? Blue or red shifted? Red shifted, which means that they're moving away from us. In fact, some are more red shifted than others, so they're moving away from us even faster. Right? But there are a couple that are blue shifted, like Andromeda Galaxy is blue shifted. So Andromeda is on a collision course with the Milky Way. One day it will collide. Amor Josiah hopping in the top 5. Zach, A-Rod, JP, Burger Place 12 with a good lead. And some reference frame in the universe, you are traveling close to the speed of light. true. Yeah. You guys see that picture up there above the door? The Hubble Deep Field. There's the edge of the observable universe. Those galaxies and us relative to each other, we're moving at relativistic speeds. I got Jordan, Amora Josiah, Zach, JP, Burger Place 12. A friend riding on the back of a truck. Okay, this is the Newtonian question. Riding on the back of a truck, going away from you at 25 kilometers an hour. The truck passes. The friend throws the ball back towards you at 55 kilometers an hour. Right? How's the? Say you catch this ball. How fast is the ball going when you catch it? The truck's headed to the right at 25. He throws the ball back to the left at 55. Yeah, 30. There you go. 30 kilometers an hour. Right? So not as fast as 30. Now, if you threw the ball forward, and then you would add that to the truck, and that would give you 80. Right? But if he throws it backwards, track. Okay, you guys get that? Right. That's the only Newtonian relativity question. All these other questions are Einstein. Ba-boom. To a person inside a spaceship moving close to the speed of light, a meter stick held horizontally inside the ship looks. So remember, we're on the spaceship. You're on the spaceship. Yeah, just same as always, right? Right. If you, okay, well, nobody picked the red one, but Earth Twin looking through a telescope thinks the answer is the red one, right? But if you're on the spaceship, yeah, you're right. The answer is the green one, right? It's the same as always. Or you don't notice anything strange about your own local environment. All right, points. To calculate how much rest energy an object contains, you multiply. What does that equation mean? E equals mc squared. Energy equals what? Oh, two winners. Mass times the speed of light squared. Guys, E equals mc squared. You guys have probably heard that floating around for years, right? Right. You guys have probably heard that since maybe elementary school. E equals mc squared, right? Now you guys get to learn what that means. E energy, right? We're talking about the energy of nuclear reactions. So whenever there's a nuclear reaction, there's a change in mass. That change in mass multiplied by the speed of light squared, boom, that's how much energy you're getting. A lot of the energy powering the lights and the air conditioning in this room right now, about 20% of it comes from that right there, nuclear. Right? Nuclear energy. JP and Burger Place, get more ports. Yeah, in time. See when we get close to it. Objects accelerate to relativistic speeds appear to you. You guys remember the train going through the tunnel the other day? All right. So, remember, do you guys remember the train going through the tunnel? Right. If the train was the same length as the tunnel at rest, but what if you send the train through the tunnel at a relativistic speed, right? Then from the mountain's point of view, it would actually get shorter. That's the opposite of the right answer, right? And if you remember the twin paradox, remember rocket twin hardly ages at all, but Earth twin ages more, right? So it's the opposite of the gold answer, right? But the one answer choice up here that actually is true is the blue answer. I have an equation and a graph to back that up too. So let me pull that out. Okay. Here's the main dilation formulas we have for time, for momentum, and for length, right? And I gave you guys the opposite choices for these two, right? But the correct answer is like this one, right? All right, and here is the same equation. You guys see this is the same equation right here, same one, right? But also a graph. Look at that. Right? So what is your momentum as a function of your speed? That's what this says, right? And Newton said, well, momentum is just mass times velocity. That's what I taught you guys last semester. That's this green line that I dashed. Right? Einstein says, well, that starts out being true for or pretty close to true for non-relativistic speeds, right? So if you're going pretty slow compared to speed of light, right? But the closer you get to speed of light, now you're hitting a relativistic speed. It deviates from Newton's prediction. You get a lot more momentum. Right? Get regular Newtonian momentum divided by this Lorentz factor. The story version of this you guys saw the last few days was if particle physicists speed up, say, like protons near the speed of light, like 99.9 something percent speed of light, you'll see them gaining this extra momentum. So that's what I'm looking for. How are we doing on points here? Got Jordan, Amor Josiah, Zach, JP, Burger Place. Ooh, more reading. Say standing on the ground, see a rocket ship move by at 95% the speed of light. Compared to the rocket being at rest, you'd see the rocket length is what? Ooh, sounds like the train going through the tunnel. Same idea. Yeah, shorter. Yeah. All right. So the train going through the tunnel from the mountain frame reference, the train where you get shorter. Same thing here. I also back that up with an equation. Right. So let's go back to like these here. Right. So here's twin paradox. Here's the one with the graph I just showed you. All right. This is going to answer that question. So what if here? Let's read the music of these equations. Let's go through a couple examples. What if you start out at rest? The ship's at rest. The train's at rest. Whatever. V is equal to 0. Guys, what is 0 squared? 0 divided by c squared is 0. What's 1 minus 0? 1. What's the square root of 1? 1, right? And then L naught times 1 is L naught. Okay, so the length would be equal to the rest length. Okay, right. So if nobody's moving, then everybody agrees on what the length of the ship is, right? But let's send the ship at a relativistic speed. So now this v is a good proportion of c, right? What does this fraction have to be bounded by? It's between what and what? If v can go up to c, v's somewhere between 0 and c. Is this between 0 and 1? Yeah, maybe it's like 0.5, for example, but it's definitely between 0 and 1. Right? If you square that, it's also stuck between those two boundary conditions. Right? Guys, what's 1 minus anything between 0 and 1? That's also bounded between what? 0 and 1, right? Like 1 minus 0.5 is still 0.5. 1 minus 0.9 is 0.1. Okay. Right? And then, guys, the square root of anything between 0 and 1, is that also between 0 and 1? Yeah. So this Lorentz factor is always stuck between 0 and 1. So if you take some rest length and multiply by something between 0 and 1, that makes it what? Longer or shorter? Shorter. Right? Shorter. More decide. Moving up. JP, Burger Place, lead. When an object is pushed to relativistic speeds, its momentum, that's the graph I was just showing you, is measured to be. Yes. There you go. Yeah, more than mv. Right. So it's the graph I was just showing you. It's that poster over there on the wall. Right. So Newtonian prediction is just plain mv. Einstein says, well, divide by the Lorentz factor, it's going to blow up more than mv. Yeah. A-Rod back in. Zach, Amor Josiah, JP, Burger Place. Over 9,000. Relativity equations for time, length, and momentum hold true for. Yeah, both of the above. This is getting an idea. Maybe I should put this phrase in here called the correspondence principle. Right. So the correspondence principle says if you come up with a new theory of how something works, then not only does it have to be able to explain phenomena that the old theory couldn't, but it also has to be consistent with maybe correct predictions of the old theory. Right. So every day at low speeds, Newtonian mechanics works perfectly fine. Right, for most situations, right? Now there are like some fringe scenarios where Newtonian mechanics kind of breaks down, doesn't fully explain what's going on, right? So you bring in Einstein physics, relativity, and Einstein relativity is able to explain things that Newtonian physics couldn't. But if you put in non-relativistic speeds, like everyday low speeds, then Einstein physics simplifies to Newtonian physics. So it covers both. Yeah, that's called the correspondence principle. More points to Burger Place. If you were to travel at speeds close to the speed of light, you would notice that your none of the above. You guys got it. Again, if you're along for the ride, you don't notice anything strange about your own locality. Yeah. All right. If Einstein's equations of special relativity are valid, they must. Yeah, all the above. There you go. All right. That's another take on correspondence principle. Right, correspondence principle. All right, you guys got that? All right, we got Jordan, Zach, Amora, Josiah, JP, Burger Place 12, and for the win, who's gonna get the Kahoot medals? 10-meter long sphere thrown at a relativistic speed. What was the 10-meter long pipe? They were both 10 meters at rest. Right? But now we got relativistic speeds going on. When the sphere passes through the pipe, the train and tunnel, it's the same train in the tunnel. Yeah. Any of the above, depending on motion of the observer, right? So how could any of these be true? Let's start with the gold one. The sphere shrinks so that the pipe completely covers it. That is true from the reference frame of the pipe. How about the red answer? The pipe shrinks so that the sphere extends at both ends. That is true from the reference frame of the sphere. If you're like riding along with the sphere, like it's like the end of Doctor Strangelove where he's riding the bomb. Or how about the blue one where they both shrink equally? Well, there is also some middle speed where that could also be true. Yeah. So to the podium with the bronze, Amora Josiah. The silver, JP. And the gold, Burger Place 12. Runners up, back in A-Rod. Stop. All right, you guys ready to do some algebra-based questions? Algebra-based. All right, so we've done most of these. We just got to hit these right here. These right here. So let's zoom in on number 12. Says, yeah. As you speed up and approach the speed of light, your length as seen by a non-accelerating observer would. Yeah. All right, so here's the length contraction formula. Let's take a look at this. Right. So if you start out at rest, so v could be 0. Right. We'll walk through this. Right. This is 0. 1 minus 0 is 1. Square root of 1 is 1. L is equal to L naught. Okay. So there's some length that matches the rest length. Right. If you're not moving. Right. Now we're gonna let v go to a relativistic speed. So this fraction is between 0 and 1. Square it. That's still true. 1 minus that is bounded between 0 and 1. Square root is bounded between 0 and 1. This Lorentz factor, this whole square root, is bounded between 0 and 1. So if you start with a rest length of like 10 meters and multiply by something between 0 and 1, that makes the contracted length, what, more than or less than the original? All right, so you guys got the answer to number 7? Okay, let's do that again. Okay, so if you start off with a rest length of like 10 meters. Let's say we're sending that train through the train tunnel, right? But we're sending it at now a relativistic speed, right? So this v is some good proportion of c, which means this fraction is between 0 and 1. If you square it, that's still true. All right, 1 minus something between 0 and 1 is between 0 and 1. The square root of that. Guys, pick any number between 0 and 1. Pick like 0.85 or whatever, right? Take the square root of that. I'll bet you it's still bounded between 0 and 1. So this Lorentz factor for relativistic speeds is going to be more than 0 but less than 1. Right? If you start off with a rest length of like 10 meters and you multiply by something between 0 and 1, what does that make this L? Right? Right? You guys got it? Okay. All right. Let's do it again. All right. So this Lorentz factor for a relativistic speed is always going to be between 0 and 1. If the original length of the train was like 10 meters, we got a 10 meter long train, right? And you multiply between 0 and 1. Let's say it's like 0.85. Let's take 10 meters multiplied by 0.85. Right. Now it's only 8.5 meters long. Right. Well, what's longer, 10 meters or 8.5 meters? Right? Okay. Right. So you guys see what's going to happen when you go to a relativistic speed? Okay, number 8. As you speed up and approach the speed of light, your mass is seen by a non-accelerating observer, right? Or I've been trying to say like momentum. Some textbooks say mass and momentum. I've been trying to switch over to momentum. It's the same idea, right? And here's the equation version. Here's the graph version. They both tell the same story, right? Just different points of view, right? So you're approaching the speed of light, right? Now, Newton would have said your momentum follows this curve, but Einstein says that's not actually true. It follows this curve. And another story you guys saw was proton is synchrotron. You speed up near the speed of light, it's a crazy huge amount of mass or momentum, depending on your perspective, right? So that is definitely going up. It's approaching infinity specifically, right? Right. Number 9. In a nuclear reaction, which of the following is taking place? Oh, that's this equation right here. E equals mc squared. It's called mass energy equivalence. So energy is equal to mass times the speed of light squared, right? Suppose you have like 100 kilograms of uranium put through a nuclear reaction. Now you only have 99 kilograms of uranium, just make it somewhat, right? You got a change in mass of like 1 kilogram. That's what was converted completely into energy. Okay? Yep. You mean all this stuff? Yeah, it's on Google Classroom. Okay. Yeah. You guys know I'm recording this video right now. You know I record this every day, right? Yeah. Yeah. So they're all every recording we've done since August is on Google Classroom. Yeah. All right. All right. Number 10. And there's the mass dilation equation, or like momentum dilation, same idea. What happens to say your mass as you approach the speed of light? Okay. Well, here's the graphical answer. Right. So as you approach the speed of light, what's happening to the mass of the momentum? It's going up to how big? It's approaching this asymptote. When you approach an asymptote, you're headed off towards infinity, right? Infinity, right? And this equation backs that up too, because the equation tells the same story. If you let v approach c, guys, what is c squared over c squared? 1. What's 1 minus 1? 0. What's the square root of 0? 0. What's anything divided by 0? Not 0. It blows up toward infinity. Right? You can say undefined. Right? Now you can never reach c. Anything with mass can never reach c. So maybe you go like 99.999% speed of light. Right? You're dividing by almost 0. Yeah, you're going to blow up really big. It's going to tend towards infinity. How about this time dilation formula, which looks like the same model, right? Same model, right? What happens when v is about 0 meters per second? Say like you're at rest and I'm also at rest. So now Earth twin and rocket twin are just standing next to each other. They're both at rest, right? How do their clock? Let's say Earth twin has a wristwatch and rocket twin has a wristwatch, but they're standing side by side. How does one wristwatch compare to the other wristwatch? Right? Well, here's rocket twin's time. Here's Earth twin's time. But rocket twin is not moving. He's not even in the rocket yet. He's just sitting around. Right? So his speed is now 0. Guys, what's 0 squared? 0 divided by c squared? 0. 1 minus 0 is square root of 1 is 1. What's t naught divided by 1? T naught, it's itself. Hey, look at that. Now Earth twin and rocket twin have the same passage of time, right? Because nobody's moving relative to each other. That's the correspondence principle. Oh, yeah. All right, so you guys got on this? Yes. Sir. All right, so I'm going to finish class with some demos. We've got one queued up on how electromagnetism is, interestingly enough, explained by relativity. All right, but that'll be a wrap on this recording, though.